Quantum invariance of knots in surfaces with boundary, knots in three manifolds with boundary. Okay, let's start today's talk. Can you please share your screen?
Yes. Wait. Oh, sorry. Okay. Uh, I start. I start. Quantum invariants of three manifolds with non-vacuous boundary. Today's title. Kalkman and me. Definition: a compact connected oriented three manifold M with boundary with the condition B is as follows. Let M be a connected compact oriented three manifold with boundary. Uh, the boundary is Z and H. G and minus H are orientation preserving diffeomorphic to a closed surface F with genus G. Fix a set of meridians M1G, MGG, respectively M1H to MG, L1, L for Z and H. That we fix meridian and longitude of G and H. We define topological quantum invariants of such M with the condition B. We sometimes write minus F as F when it is clear from the context. The three manifold with two connected boundaries, and both are diffeomorphic. Definition 0.2. Let F be a connected cross-oriented surface. Let L be a link in F cross interval. Take a natural projection of Ki to F cross minus 1. Call the resultant immersed circle Pi. The projection of L to F cross minus 1. Take an image of regular homotopy from Ki to Pi. Ki to Pi projection, take projection. By using it, we can define framing for Ki. Thus, we can define a frame to link in a second surface by using L. Of course, L framed L represents a compact oriented three manifold with boundary that is disjoint union of the same two surfaces F and minus F. It also represents a four manifold, the surgery or attaching four-dimensional two-handle along frame to link. The second surface and link there, and by this case, we can define framing. It's an example. This is second torus, and there is a link And in this case, using projection, there is an immersed annulus, so we can define framing even if not is a non-vanishing cycle. Definition 0.3, define F cross interval with the condition F as follows. Fix a set of meridians and longitude for F, and longitude cross plus 1 and longitude cross minus 1, meridian cross plus 1, meridian cross minus 1. We fix meridian longitude for each boundary. A frame to link L frame in F cross interval with condition F represents a compact-oriented three-manifold with boundary F and F with the condition B. It also represents a four-manifold. We fix boundary. We fix the morphism map of boundary of three manifold. If a frame to link L in F cross interval represents a simply connected four manifold, we call L is a frame to link with condition S for simply connected. Anyway, the condition is a little long, so abbreviate S. The frame to link in secant surface represents a four manifold in the connected four manifold in general.
Excuse me. By a framed link, you mean that we have just band? Yes. So we don't write any numbers, but we should draw a two-dimensional thing inside, right?
Wait, please wait.
What do I mean? What is the definition of a frame link?
Okay, a little conceptual figure, but F cross I.
Okay, well, this is a band, as you okay.
Band. So yes, the F secant surface cross interval make four manifold, and along frame to link we attach four-dimensional two handle with.
Yeah. So you mean that you have bands? You mean that you have bands, right?
But bands. What bands?
Well, so how do you define a framed link? If you just say that you have a number, it would not suffice.
Integer. Framing with integer.
No. It's not. I think it's not sufficient if you have if you have a non-trivial homology class. Yeah, if it's not trivial, yeah. Do you think that just writing an integer number will suffice?
We can do that because it's a little conceptual.
Yeah, I think so. Yeah, maybe.
K, there is K. Take projection There may be there may be intersection, but uh, by using this band annulus, uh, count count uh, count the number. It is framing. We can define framing. Yeah, yes, that we think framing, we think projection and use band or immersed annulus and define framing and framing.
Okay.
And by using this framing, we attach four-dimensional two-handle. We get a four manifold. In general, it's not simply connected, but if L framed link represents a simply connected four manifold, then we call L is framed link with condition S for simply connected. This condition is important. We generalize the results in Kirby, Fenn, and Rook, and Roberts. We prove the following. M be a connected compact-oriented three-manifold with the boundary F and F, with the condition B, the fixed median longitude. Then M is always described by a framed link in F cross interval with the condition F, the fixed median longitude, and with the condition S. It's important. The M is the three manifold can be represented by a framed link with condition S. We generalize the results in Kirby, Fenn, Rook, and Robert again, and we prove the following. Let F be a connected closed-oriented surface. Let M be a connected compact three-manifold with boundary F and F, with the condition B, the fixed median longitudes. Let FR and FR prime, LFR prime be framed links in thickened surface with the condition F fixed medians and longitudes, and with the condition S simply connected four manifold, which represent M. Now, there are infinitely many such L. So take two arbitrary framed link with condition S. Then two framed links are L frame is made from L framing prime by a finite sequence of handle slide, blow up, and blow down. That is Kirby moves. This is important, I think. If we don't suppose the condition S, simply connected connection in theorem, L is not made from L prime by a finite sequence of Kirby moves in general. Example is, oh, sorry, it's not fine. Can you see it? This is thickened surface, sorry, thickened torus. And longitude, red one is longitude and the blue one is linked once in thickened torus. And this is empty. There is no framed link, only secundus torus. They three manifolds are same. Both represent the same three manifold, but they are not changed into each other by Kirby moves. Kirby pointed out Fenn and Luke Roberts answered his suggestion, Kirby's suggestion. So in general, Kirby moves are not enough, but that's a point. It is a point. If both L satisfies condition S, then both are changed into each other by Kirby moves.
So, and how do we see that the condition S is not satisfied?
If S, S is enough, if the condition S is enough, we need the condition S because
so what is not satisfied here? So,
roughly speaking, if they are Kirby move equivalent, both represent the same four manifold. Two, not only three manifold, but also four manifolds are same.
Okay,
but,
okay.
But the pi one, there is no pi one because we attach 200 here.
Okay, okay.
Yeah, that's the point.
Okay.
So we need to order operation 3. So in general, we need this operation. Such circle disappear. Kaufman. Oh, next topic. Kaufman invented virtual links. The Jones polynomial of virtual links is defined. We can regard any framed link in second surface as a virtual framed link. Die Kaufman for virtual framed links. Note that the linking number of any pair is defined. The value is integer or half integer. Note that the framing is an integer. Framing is always integer, but linking number is half integer. Quantum invariants of framed virtual links are defined by Die and Kaufman. If two framed links are changed into each other by a sequence of Kirby moves and classical and virtual Rademacher moves, each quantum invariant of L is equivalent to that of L prime. Die and Kaufman defined framed virtual links, and they define quantum invariants of framed virtual links. And they proved Kirby moves if they change into each other by Rademacher moves and Kirby moves, their invariants are the same. This is an example of a virtual framed link. One way of saying today Today's talk give a meaning of three manifolds of this invariant. Uh, Definition 0.8. Let F be a connected closed-oriented surface. Let M be a connected oriented compact three manifold with the boundary F and F with the condition B that give fixed meridian and longitude in each F. Let L in secant F cross interval with the condition F, the F means fixed meridian and longitude, be a framed link with condition S, which represents M. And always such L exists. Always for any M, there is a framed link L with condition S. Regard L as a framed virtual link. Define quantum invariants of M to be Dye-Kaufman quantum invariants of the framed link. Main theorem, this definition is well defined. That is, each of the quantum invariants of M is a topological invariant. Application L be a two-component one link in S3. The complement has the boundary T2 and T2. A pair of meridian and longitude is defined naturally because meridian and longitude of two components. It has our quantum invariant. This three manifold, the complement is a three manifold with boundary T2 and T2, and there are natural meridian and longitude. So complement has our quantum invariant. Let K be a one knot in S3. Make a two-component split link made from K and the trivial knot. Of course, there are other natural ways to make a two-component one link from K. This invariant produces a classical knot invariant.
Excuse me, a two-component split link. Yeah, with the trivial knot. Excuse me, but don't you think it will be just the usual invariant of the knot? It's quite important. So if we take a split link, then do you think that this split component will give any impact which is significantly different from the usual quantum invariant that we have? Well, I can understand, for example, if you would consider the Hopf link and get a thickened torus. We can have a Hopf link. But then we will have a three-component link. But I don't see how you can get an invariant of just a knot, not a link. It's crucial for us.
I just to say, oh, sorry. For example, trifoil knot.
Yeah.
We just consider two components make two component link. We can always make two component link K and T.
Yes. But you pretend that you have some new invariants. I think that the way you are constructing the trefoil knot will live just in a domain. It will live just inside a three ball. It will live just inside the three ball and will have nothing to do with this split component. So I think you will get just usual quantum invariants of classical knots which have nothing to do with this knot, with this torus.
The value must be defined.
No, it may be defined, but I don't think there will be anything new at all.
For example, if we forget this part, and if we
I don't see why you can have anything new. So you see, we are greatly interested in new invariants of classical knots one can get from virtual knots.
Yeah,
but if it is split, I don't see any way how this torus can interfere into counting this invariant of K.
The boundary is two torus.
Okay. So, okay, yeah. Okay, now I see, yeah, and then it's great, yeah, okay. Yeah, it's, okay.
And probably virtual knot people must be delighted. We use virtual knots and make new invariant of classical knots in this case.
Okay, yeah, and that way it will be really great. So do you have any examples? Have you calculated any examples?
Oh no, no, I'll do that.
But you see, this idea is really great. Maybe do you have any feeling about possible cobordisms? Do you have any feeling about possible cobordism invariants coming from that? Because it will be really interesting to see how it behaves under cobordisms.
Oh, yeah, I'm working with a little, but I have not considered so much because
you see this idea is really great. Yeah, this idea is really great.
Thank you. Oh, yeah. Yeah. Anyway, three manifold to three manifold. We consider complement and complement. The boundary is to torus and torus. The boundary is torus and torus. Cobordism, not cobordism, gives a cobordism four manifold from M to M prime.
Yeah.
We must consider it. Yeah, I'm thinking about it. Thank you. Okay, and probably some readers will wonder the following question. Dye-Kaufman quantum invariants of framed virtual lengths are virtually equivalent. How do we interpret in our situation? What is virtual three manifold? it framed virtual links are based on virtual links, so there are virtual equivalent, 100 equivalent. There are 100. There are 100 stabilizations, of course. So what means in our situation?
Well, I think you may. I think it would be worthwhile for you to recall a little bit from the work of Diane Kaufman. I mean, all that stuff with John Swenslide important. I'm not sure that our seminar, all people remember here.
Okay. Anyway, we give one answer. Virtual three manifold. What is virtual three manifold? F
Yeah.
and B F prime be a connected cross-oriented surface. M and M prime be a connected compact-oriented three manifold with boundary F and F, or F prime and F prime with condition B, fixed meridians and longitude. Let L or L prime be a framed link in F, second F, or second F prime. Forget framings for now. Assume L in F is virtually equivalent to L prime in F, second F prime. That is, suppose that L in F, second F is made into L prime in second F prime by a different map of F and handles stabilizations. We say that M and M prime represent same virtual three manifold. I show an example. Second torus and framed knot. It represents a three manifold. Virtual stabilizer equivalent, 100 equivalence, 100, sorry, 100 stabilization. We get cross-oriented surface with genus 2. And forget framing once, they are virtually equivalent. They both represent the same virtual knot. And both represent different three manifolds, but two three manifolds have this relation. We call these two three manifolds are virtually equivalent. Roughly speaking, three manifold and this stabilization.
Do you have a notion of virtually equivalent for manifolds?
Then it second surface and cross I, consider second surface cross I and regard it represents four manifold, it represents four manifold. Probably it makes sense. Regard it four manifold, and this stabilization makes equivalence relation. I think it makes sense.
Okay.
Anyway, we define virtual three manifold. And it's trivial, our theorem and Dye-Kaufman theorem, each of our quantum invariant is an invariant of virtual three manifold.
Yeah.
So we get invariant of three manifold and that of virtual three manifold. Oh, sorry. Dye-Kaufman is here. Fenwick and Kaufman's virtual knot and Kirby's popular papers and Roberts proved this one. why condition S simply connected condition works. I explain why condition S is important. We are given M, the boundary is F and F, and fix meridian longitude. And take second F. There is by cobordism theory, there is a compact oriented four manifold whose boundary is M and F, second F. The M and second F makes a closed oriented three manifold. So there is it bounds compact oriented four manifold. There are infinitely many kinds of V and V prime. By Roberts, Kirby, Fenn, and Luke, we can suppose there are simply connected V and V prime. First, blow up and blow down to F. Frame to link, add +1 trivial knot -1 trivial knot. We can change signature of V and V prime. We can suppose signatures are same. By cobordism theory, it's closed oriented four manifold, V and V prime. We attach V and V prime at the boundary. And we can suppose signatures are the same. So there is 5 manifold. Compact oriented 5 manifold. Further, cobordism theory and handle decomposition theory, W has such handle decomposition, only 2 handles and 3 handles. We can change 1 handle to 3 handle. We can change 4 handle to 2 handle. And the V 2 handle and 3 handle and the V prime. What is P here? P is made from V by attaching 5-dimensional 2 handles. It is very important. We suppose V is simply connected. So 2 handle, the attaching part is contractible circle. So P is V connected sum S2 cross S2 or twisted cross S2. In the same way, P is connected sum of V prime and sorry, S2 cross S2 and S2 twisted cross S2. They are different. So L framing and L and L prime represent the same M and satisfy condition S. L and these represent diffeomorphic four manifolds. And by self-theory in Robert's paper, written in Robert's paper, they are handle sliding equivalent. So they are Oh, that's outline. So under so that therefore L and L prime in secant surface with the condition F median longitude with the condition S, L and L prime with the condition S represent M. Then L and L prime L is made from L prime by a finite sequence of handle slide, blow up, and blow down. That is curving moves. This is important step. Let's review Robert's theorem.
Excuse me. By the way, let's try to tackle something. For example, we have a Conway knot, right? And recently it was proved that the Conway knot is not slice. So let's try to represent the Conway knot by using your technology. And let's try to prove that it's not slice.
Oh, okay. Yeah, I will try.
Okay.
But yeah, okay. Oh, but calculation may be complicated. But yeah,
Yeah,
I will
sure,
try.
sure. But
yeah, thank you. Yeah, and further, yeah, and yes, but roughly speaking, we have to consider this discussion. M and M prime, 3 manifold and 3 manifold, and there is 4 manifold. We know quantum invariant of M. We know quantum invariant of M and M prime. If there is a good 4 manifold, but do you know a relation of quantum invariant of both in this situation? Are there good relation between quantum invariant of M and M prime? Yeah, we have to think about it. And probably very different from different viewpoint. Anyway, for not cobordism, sorry, cobordism invariant, sorry, not cobordism invariant from Jones and quantum invariant is maybe we know Rasmussen invariant only. Maybe it's only one. Quantum invariant.
There are some invariants from Orzhov-Szabo Higger-Floer homology.
Kobanov homology, Rasmussen invariant.
No. I think besides Rasmussen, there is Orzhov-Szabo invariants. Orzhov-Szabo, I mean, there is something like tau invariant coming from Higger-Floer homology.
I talk about Rasmussen invariant. It is made Rasmussen invariant made from Kobanov homology. not flare homology. The Rasmussen invariant is related to John's polynomial, so it is one candidate. Maybe related. Anyway, thank you. Okay, I will think about the cobordism invariant. Cobordism invariant from our invariant. We
Okay.
have. Do I have 1 hour or 1 hour or 90 minutes?
Yeah, usually it's 90 minutes, but it's okay for you to have 1 hour. We understand that in Japan it's late now.
Okay. We have time, so let's review Robert's theorem.
Yeah.
Let M be a compact oriented. I cited from review Robert's paper. M be a compact connected orientable three manifold with boundary containing a framed link. Doing surgery on this link produces a new manifold whose boundaries canonically identifies the original boundary M. The strictly to say we fix the map of the boundary. In fact, any compact connected orientable N whose boundary is identified with that of M. So we fix the homomorphism map of the boundary may be obtained by surgery on M in such a way that the boundary identification obtained after doing the surgery agrees with the chosen one. For an arbitrary compact connected orientable three manifold with boundary moves O1, O2, O3 still surface. O1, O2, O3 this one. So we need this. We need O3 in general. But usually Kirby moves are these one. And Dye-Kaufman invariants are Dye and Kaufman proved their invariant doesn't change under these operations. So we excluded this move by introducing condition S. And, I said this is important step. The both two framed links in sequence surface with condition S simply connected. They are Kirby move equivalent. I said M be a connected compact oriented three manifold with a boundary with fixed meridians longitude. M is always described by a framed link in sequence surface with condition S. This is important too. Always there is a framed link with condition S, simply connected. We proved it. The idea is as follows. this is a part of second surface, and there are, of course, there are frame to link. I omitted, but there is a frame to link, a part of frame to link. We put these four nodes here, so that it doesn't touch original frame to link. Robert's theorem, this operation doesn't change three manifold. So three manifolds are the same, but we kill this generator of pi 1. That's a proof.
Well, excuse me, can I see the picture again?
Okay.
Okay, so and how do you add do you stabilize it twice? So do you add two pairs of
Yes. Four circles and 2 times of O3.
okay, okay,
The 1 times of O3 includes 2 circles.
okay.
Yeah, and next IX. Oh, sorry. Oh, next I explain. In this manifold, we can suppose there is. We can suppose that there is no one handle. We can suppose there is no one handle. Why we can do that? Very low dimensional example. Two circles, 2s1. It bounds for also. Two circles bounds two manifolds. This is 0 handle. This is 2 handle. But if there is such one, two circles bounds 0 handle and 0 handle. Zero handle and 2 handles changed to 0 handle and 0 handle.
Yeah, it's called trading handles.
Yeah, yes. By using, in this case, we use 3-dimensional 2 handles. And so generalize this operation into high dimensional case. H1 and H0, n-dimensional 0 handle and n-dimensional 1 handle is S1 cross dn minus 1. It changes D2 cross Sn minus 2. So it becomes 0 handle, n-dimensional 0 handle, and n-dimensional n minus 2 handle.
So isn't there a parity issue? I mean, so we can trade 0 for 2, but can we trade 0 for 3? So isn't there a parity issue, parity, dimension parity?
N minus 2.
Yeah, I'm asking, well, does it work nice for both even and odd and never mind the parity of dimension?
Yeah, n is a natural number.
Okay.
So if n is 4, 1 handle becomes 2 handle.
Okay.
If n is 5, 1 handle becomes 3 handle.
Great.
Yeah, so that's the reason. There is 4-dimensional compact-oriented manifold. First, there is 1 handle, 2 handle, 3 handle. But we can change 1 handle to 2 handle. And 3 handle, the dual of 3 handle is 1 handle. It becomes dual 2 handle. Dual 2 handle of dual 2 handle is 2 handle. So we change all 1 handles and all 3 handles to 2 handles. So we can, so Roberts, Kirby, Fenn, Luke, the theorem needs only 2 handles. And in our case too. Yeah, M in our case too, M with boundary F and F, fixed median longitude. Only 2 handles, we can represent M by using only 2 handles, frame to link, only 2 handles. And further, we can suppose, or we always suppose L represent simply connected to 4 manifold. And by using such frame to link, Dye-Kaufman invariant is topological quantum invariant of M. That's our main theorem.
Okay.
So I talk all. I talked all. I prepared.
Yeah. It's well. The result is really great. So thank you very much. I really enjoyed it. Yeah,
thank you very much.
I really enjoyed it. Well, actually, yesterday, of course, we should try to calculate it, and we should try further applications of the results. And I'm sure there will be applications,
Yes.
especially for classical knots. So you see, the main scope of ours is the breakthrough by using virtuals for classical purposes.
Yeah. I'm glad too. Yeah, I know you will be glad.
Yeah, and yesterday we were discussing with Luke Kaufman. So we were discussing various approaches, and actually, possibly, of course, quantum invariants with the Jones-Wenzel idempotent are a great thing. But yesterday we were trying to do some simple things like determinants and maybe some other generalizations. And I think that such additions like not components may give quite a lot. And yesterday we were discussing some ideas about quadratic forms, how they give invariance of 3 manifolds, invariance of 4 manifolds. And I think Son John can collect what we were discussing yesterday and grant it to you. And I think we can try to use some easier things. Of course, it's great to understand complicated things like Jones-Wenzel projection and written Reshetikhin-Turaev invariance, but we would be very happy to do some easy things as well. And I think Son John will share our yesterday's thoughts with you. So thank you very much again.
Oh, yeah, thank you. Me too.
Okay, dear colleagues, are there any questions or comments, remarks? So please.
Oh, yeah. One comment is we fix meridians and longitude. Of course, Roberts did it because one reason is if we don't fix the diffeomorphism map of the boundary, we cannot take unique M. That we want M be unique, so we must fix diffeomorphism of the boundary. But we can say one thing from another viewpoint. Quantum invariants of 3 manifold with boundary Atiyah said that if we the Atiyah's axiom Atiyah's TQFT axiom quantum invariant of manifold with boundary must be linear map from vector associated F to vector space associated with G. Then we consider element of VF and VZ. Probably the fact we fix meridians and longitudes correspond to this fact. Quantum invariant of manifold with boundary is linear map, not only one complex number.
Yeah.
So it's a linear map, so there are n cross n, many numbers. So we change the meridian longitude, the value may be changed. So probably they are related. It's natural to fix meridian and longitude from this viewpoint.
Okay.
Yes, I can finish.
Okay, thank you. Colleagues, any questions? Unmute your microphones right on the chat line. Well, if it's not the case, so let's thank Eiji again for his ability to give a talk so late. It's really great for us. So we
Thank you.
enjoyed
Thank
it.
you.